Welcome back to Blueprint Zero, the channel that goes behind the classified doors and into the labs where the future of warfare is forged. We often see the end result, the cutting-edge fighter jet, the revolutionary missile system, the game-changing piece of battlefield tech. We hear about the massive defense contracts, the corporate giants, the years of development. It all seems so planned, so inevitable, so expensive. But the history of military innovation is rarely that neat. It's often messy, chaotic, driven not by committees but by individuals. By lone wolves, persistent dreamers, maybe even disgruntled engineers working after hours, fueled by lukewarm coffee and the burning conviction that there has to be a better way. Tonight we pull back the curtain on one such story, a tale that bridges the gap between a moment of quiet desperation and a multi-billion-dollar technological revolution. It's about an engineer buried deep within the bureaucratic labyrinth of a major defense contractor, wrestling with a problem that was costing millions, threatening careers, and potentially compromising national security. The official teams, the senior experts, were stuck, throwing more money and manpower at solutions that were hitting a dead end. But this one engineer, working late, frustrated, saw something they didn't. An insight born not from complex simulations, but from a simple, elegant idea, captured in a rough sketch during the quiet hours. That sketch wasn't just ignored. It was initially dismissed, maybe even ridiculed. But it held the seed of something transformative. This is the incredible story of how one engineer's late-night sketch turned into a billion-dollar defense contract. Before we dive into the schematics, if you believe that true innovation often requires challenging the status quo, and that these stories of intellectual courage deserve the spotlight, then I need you to join our R&D team. First, hit that subscribe button and activate the notification bell. It ensures you receive all our project updates. Second, give this video a like. Your engagement fuels our research. And finally, drop a comment down below. Let us know what country and city you're tuning in from. Our global network of tech and history enthusiasts is what makes this channel thrive. All right, sharpen your pencils. Let's get to work. My name is Dr. Evelyn Reed, though back in 1983, the doctor part felt more like an administrative footnote than a badge of honor. I was a mid-level systems engineer at Vanguard Aerospace, one of the behemoths of the Cold War defense industry. My world was supposed to be one of cutting-edge innovation, of pushing the boundaries of technology to keep America ahead of the Soviet bear. In reality, it was mostly a world of endless meetings, soul-crushing PowerPoint presentations. Even back then, we had primitive versions, and the constant, grinding pressure of Project Chimera. Chimera was Vanguard's white whale, our ticket to decades of guaranteed government funding, our chance to leapfrog the competition. It was a next-generation air-to-air missile system, designed to be faster, smarter, longer-ranged, and more resistant to countermeasures than anything currently flying on either side of the Iron Curtain. The Air Force had poured hundreds of millions into it already, and the pressure to deliver a working prototype was immense. The problem: Chimera wasn't working. More specifically, the guidance system wasn't working. The missile body itself was a masterpiece: sleek, powerful rocket motor, advanced aerodynamics. But the brain, the intricate dance of radar seekers, inertial navigation units, INUs, and control surface actuators, it was a disaster. In test after simulated test, the missile would lose lock, get confused by electronic countermeasures, ECM, or simply fail to make the microsecond-fast calculations needed to intercept a maneuvering, high-G target. The senior engineers, legends in the field who had designed the systems for the Phoenix and Sparrow missiles, were baffled, frustrated, and increasingly desperate. Their approach was fundamentally conventional. Throw more processing power at it. Faster chips, more complex algorithms, bigger radar dishes crammed into the missile's already tight nose cone. It was an arms race within the missile itself. More processing power demanding more electrical power, generating more heat, requiring more complex cooling, adding more weight, reducing range and maneuverability. They were hitting a wall of diminishing returns, pouring millions into incremental improvements that weren't solving the fundamental problem. My role in this multi-billion-dollar fiasco: I was officially assigned to the Environmental Testing and Integration Subcommittee. Translation: I was the guy who made sure the connectors didn't corrode in salt spray and that the circuit boards could survive the vibration of launch. It was necessary work, but mind-numbingly dull for someone who had earned her PhD studying adaptive control systems and neural networks, concepts considered pure science fiction by most engineers in 1983. I was a square peg in a round hole, a theorist trapped in a world of practical, increasingly frantic hardware integration. I attended the endless Chimera Guidance System review meetings, sitting silently in the back, listening to the same arguments, the same proposed fixes. Add another processor, tweak the Kalman filter, increase the radar pulse repetition frequency. It all felt so brute force, so linear. They were trying to build a perfect, deterministic machine to solve an imperfect, chaotic problem. The air battle of the future wouldn't be a neat equation. It would be a swirling, dynamic mess of high-G maneuvers, stealthy targets, and sophisticated electronic warfare designed specifically to confuse deterministic systems. Their smarter missile brain was just becoming a bigger, more complex target for enemy ECM. What if the answer wasn't to make the missile smarter in the conventional sense? What if the answer was to make it dumber, or rather smarter in a completely different way? My frustration festered. I knew instinctively that their path was a dead end, but I was Dr. Reed, the junior environmental tester, the woman with the impractical PhD in futuristic control theory, voicing my concerns, let alone proposing an alternative, in that room full of gray-haired, cigar-chomping missile design legends. It would be professional suicide. They'd laugh me out of the room, dismiss me as a naive academic who didn't understand the real-world constraints of hardware, budgets, and deadlines. So, I kept my mouth shut. But I couldn't stop thinking. Late at night, long after the fluorescent hum of the main engineering bays had faded, I'd sit in my small, sterile cubicle, surrounded by printouts of failed simulation runs, the official Chimera schematics spread out like a map of a doomed expedition. I wasn't looking at the connectors anymore. I was looking at the architecture, the central processor, the powerful, dedicated radar seeker, the complex inertial navigation unit, all feeding data into one overburdened electronic brain, trying to calculate the perfect intercept solution. What if the problem wasn't the power of the brain, but the reliance on a single, primary sensor? The active radar? Active radar was powerful, yes. It painted the target with energy, providing precise range and bearing. But it was also a beacon. The moment that radar lit up, the target knew it was being hunted. It could deploy countermeasures, start jamming, initiate evasive maneuvers. The missile gave away its biggest advantage: surprise. The moment it tried to get its primary data feed. What if the radar wasn't the primary sensor? What if it was just one sensor among many? What if the missile relied initially on passive sensors? An infrared IR seeker, perhaps, looking for the heat signature of the target's engine. An electronic support measures ESM receiver, listening for the target's own radar or communication signals. Even a simple optical sensor, a tiny camera, looking for the visual shape against the sky. These passive sensors wouldn't give you the pinpoint accuracy of radar, not initially, but they were silent. They allowed the missile to track the target covertly, without revealing its own presence until the last possible second. But how do you guide a missile accurately using only fuzzy, imprecise, passive data? That was the multi-billion-dollar question. The answer, I started to believe, wasn't a better algorithm running on a faster central processor. The answer was sensor fusion, and not just fusing data in one brain, but distributing the processing. What if each sensor, the radar, the IR seeker, the ESM receiver, had its own small dedicated microprocessor? Each sensor brain would process its own data stream, filtering noise, identifying potential targets, calculating probabilities, and then these distributed processors would talk to each other, sharing their fragmented, uncertain pieces of the puzzle, collaborating to build a unified, high-confidence track on the target before the main radar even needed to light up. It was like a team of detectives, each with a different clue, pooling their information to identify the suspect. The radar would only need to be used sparingly, perhaps in the final terminal phase for a precise intercept, or to burn through heavy jamming. The missile would be quieter, stealthier, more resistant to countermeasures because it wasn't relying on one single, easily fooled sensor. It was a distributed, multispectral, collaborative guidance system. It was elegant. It was different. And it was probably impossible to build with 1983 technology, at least according to my bosses. One particularly frustrating Tuesday night, after yet another disastrous Chimera simulation review meeting where millions were allocated to upgrade a radar processor that I knew wasn't the core problem, I found myself staring at a blank sheet of paper on my desk. It was actually the back of a cafeteria napkin, stained with coffee rings. I picked up my pen, not to write equations, but just to doodle, to vent. I started sketching the missile, not the sleek aerodynamic body, but the brain. I drew the central processor, the big, overburdened king. Then I drew the sensors around it, radar, IR, ESM. I drew the data lines flowing into the central brain. This was the current failing architecture. Then, on impulse, I started erasing. I erased the direct lines from the sensors to the main brain. Instead, I drew small separate boxes next to each sensor. Little local processors. I drew lines connecting them in a web, a network, data flowing between the sensor brains. Then only a single, refined target track line going to the main flight control computer, which now only had to worry about flying the missile, not finding the target. It was a mess, a crude, coffee-stained schematic of a distributed network architecture. It looked like a child's drawing of a spiderweb. It completely violated the established principles of centralized processing and control. It would require multiple, synchronized microprocessors, complex data sharing protocols, sophisticated sensor fusion algorithms, all crammed into the tiny, power-constrained, high-G environment of a missile nose cone. It was, by the standards of the day, utterly, completely stupid, impractical, unbuildable, a fantasy. I stared at the napkin, and I knew, with a certainty that chilled me to the bone, that this stupid, impossible sketch was the answer. This was the key to unlocking Chimera. This was the future of missile guidance, and nobody would ever let me build it. That coffee-stained napkin became my secret Bible, my Rosetta Stone for a future that existed only in my head, and, increasingly, in the sprawling, chaotic simulations I started running on Vanguard's aging mainframe computer during the graveyard shift. Getting access wasn't easy. Mainframe time was jealously guarded, allocated based on project priority, and Dr. Reed's pet theory on sensor networks had a priority level somewhere below, optimizing the cafeteria menu. But I learned the system. I learned which sysadmins were overworked and prone to overlooking unscheduled batch jobs submitted at 3 a.m. I learned how to disguise my complex sensor fusion algorithms as routine environmental stress analysis calculations. I became a digital ghost, haunting the periphery of the official Chimera project, using their own tools to undermine their failing philosophy. The napkin sketch was the concept. The simulations were where the brutal reality hit. Building a distributed processing network inside a missile in 1983 wasn't just hard, it bordered on the impossible with the available technology. The microprocessors available off the shelf, the Intel 886 or Motorola 68000s, were laughably underpowered compared to the custom-built behemoths in the main Chimera guidance computer. Memory was measured in kilobytes, not megabytes or gigabytes. The idea of having multiple independent processors, each running complex filtering and correlation algorithms, and communicating with each other in real time over a reliable data bus, all while surviving 50 Gs of acceleration and extreme temperature swings. It was absurd. My initial simulations were crude, focusing purely on the logic. Could a network of simple, dumb processors, each receiving noisy, incomplete data from a simulated passive sensor, IR, ESM, collaboratively build a more accurate target track than a single, powerful processor relying solely on a simulated active radar that was being actively jammed? The answer, even in those early rudimentary runs, was a resounding yes. The network was inherently more resilient. If one sensor was jammed or spoofed, the others could compensate, cross-correlating their data, identifying the outlier, maintaining the track. The network could learn, adapt, prioritize information based on confidence levels. It wasn't just processing, it was rudimentary cognition. But translating that beautiful simulation into something physically buildable was another matter. I spent months wrestling with the hardware limitations. How could I synchronize the timing between multiple independent processors with microsecond accuracy, crucial for data fusion? How could I design a data bus robust enough to handle the information flow without becoming a bottleneck or an electromagnetic interference nightmare? How could I cram all this extra hardware, multiple processors, interface boards, power regulators, into a space already overflowing with the existing sensor packages and warhead? The official Chimera team was struggling to fit one super processor. I was proposing 3 or 4 smaller ones, plus the interconnects. I became a hermit, fueled by vending machine coffee and the burning conviction that I was right. My colleagues in environmental testing treated me with a mixture of pity and annoyance. I was clearly not a team player, off in my own little world, neglecting my official duties, which I performed just well enough to avoid getting fired. Rumors circulated. Reed's lost it. She's still tinkering with that crazy network thing. Thinks she can out-engineer the entire guidance division. I knew I needed allies, but who? Going back to the senior leadership was unthinkable. Talking to the main Chimera guidance team would be like handing my secrets over to the enemy. They'd either steal the concepts and butcher them, or use them as further evidence of my incompetence. I needed someone on the inside, someone who understood the hardware, the limitations, the frustrations of the current approach, but who wasn't part of the established hierarchy. I found him in the integration lab, a place filled with the actual guts of the Chimera missile prototypes, racks of circuit boards, bundles of wiring harnesses, test sets blinking with cryptic diagnostics. His name was Ben Carter, a senior technician, not an engineer with a fancy degree, but a man with 20 years of hands-on experience making complex electronics actually work. He was quiet, meticulous, universally respected by the engineers because he was the one they secretly went to when their elegant designs inevitably failed to survive contact with reality. Ben saw the failures firsthand. He saw the blown capacitors, the fried processors, the inexplicable glitches that plagued the Chimera guidance system day after day. He didn't understand the complex algorithms, but he understood hardware. He understood heat dissipation, signal integrity, power management, and he was deeply, profoundly unimpressed with the official approach. I approached him cautiously, not with my grand theory, but with a specific, practical problem. "Ben," I said one afternoon, finding him hunched over a particularly troublesome radar interface board, "I've been running some environmental simulations, hypothetical of course, on multi-processor architectures for redundancy. I'm hitting a wall on heat dissipation in a confined space. Any thoughts?" It was a carefully crafted opening, appealing to his expertise, hinting at my area of interest without revealing the heresy. Ben looked up, wiping his hands on a rag, his eyes sharp behind his safety glasses. He knew exactly what I was doing. He'd heard the rumors. But instead of dismissing me, he just grunted. "More processors, more heat. Basic physics, Doc. You trying to build a toaster oven or a missile?" He paused, then pointed with a screwdriver. "Official guys. They're trying liquid cooling. Complex. Heavy. Another failure point. Stupid. So what's the alternative?" I pressed. He shrugged. "Depends. What kind of processors? How much power? Where's the airflow?" That conversation was the beginning. Over the next few months, Ben became my unofficial, unwilling, and deeply skeptical co-conspirator. I never showed him the napkin sketch. I never told him the full scope of Project Spiderweb, as I'd started calling it in my head. I just kept coming to him with hypothetical problems, specific technical hurdles related to synchronizing clocks between multiple boards, designing a fault-tolerant data bus, minimizing electromagnetic interference between densely packed components. He'd grumble, he'd curse the pointy-headed academics, but then he'd offer solutions. Practical, elegant, workable solutions, born from decades of troubleshooting real-world hardware. He suggested using fiber optics for the data bus, faster, lighter, and immune to EMI. He showed me new techniques for thermal management using heat pipes, still experimental but far simpler than liquid cooling. He even pointed me towards a new generation of radiation-hardened microcontrollers being developed for the Strategic Defense Initiative, Star Wars program, still underpowered compared to the Chimera's main brain, but tough, reliable, and designed for distributed applications. Ben never asked why I was working on this. He didn't need to. He saw the daily failures of the official project. He knew something different was needed. And maybe, just maybe, my crazy ideas weren't entirely crazy. The real breakthrough, the skunkworks moment, came from failure. Chimera's failure. One of the major subcontractors responsible for the inertial navigation unit went bankrupt. Suddenly, Vanguard was scrambling. The existing INU was now an orphan, unsupported. A new INU would take months, maybe years, to integrate. Project Chimera, already behind schedule and over budget, was facing a potential death blow. Panic swept through the program office. But for me, it was an opportunity. Buried in the assets acquired from the bankrupt subcontractor was a piece of hardware considered obsolete, useless, an early prototype strap-down inertial measurement unit, IMU. Unlike the complex, gimbaled INUs used in Chimera, a strap-down IMU used simpler, cheaper gyros and accelerometers fixed directly to the missile body. Its raw data was noisy, inaccurate, unless you had sophisticated software algorithms to process it, to filter the noise, to compensate for the sensor drift. Algorithms that were remarkably similar to the sensor fusion and filtering techniques I was already developing for Project Spiderweb. And crucially, this prototype strap-down IMU had its own dedicated, albeit primitive, microprocessor. It was, in essence, a self-contained, smart sensor node, exactly what my distributed architecture needed. Through Ben, who was tasked with cataloging the acquired junk, I managed to divert the prototype IMU. Officially, it was marked as non-functional, scrapped. Unofficially, it became the centerpiece of my hardware demonstrator. In my bunker-like cubicle, surrounded by scavenged parts and fueled by a growing sense of urgency, I built it. Not a full missile guidance system, but a proof of concept for the core idea. Sensor fusion in a distributed network. I took the strap-down IMU with its noisy data stream. I took a simple, off-the-shelf infrared camera, the kind used for industrial inspections. I interfaced both of them, not to a single central brain, but to two separate, cheap microcontrollers, my local processors. I wrote code for the IMU processor to filter its own data, providing a rough estimate of orientation and movement. I wrote code for the IR processor to scan its field of view, identify potential hotspots, and estimate their bearing. Then I connected these two processors via a simple serial data link, my rudimentary network. And I wrote the fusion algorithm running on both processors, allowing them to share their uncertain data, cross-correlate it, and collaboratively build a single, higher confidence estimate of the target's position and the system's own orientation, far more accurate than either sensor could achieve alone. It was Project Spiderweb in miniature, built with literal garbage. One night, it worked. I pointed the IR camera at a hot soldering iron across the room. On my monitor, fed by the data link, I saw two things: the IMU's wavering estimate of straight ahead, and the IR camera's fuzzy bearing to the heat source. Then, as the fusion algorithm kicked in, a third symbol appeared, a stable, high-confidence vector, pointing directly at the soldering iron, correcting for the IMU's drift using the IR data, and confirming the IR's bearing using the IMU's orientation. It was fusing, it was collaborating. The stupid prototype, the network of dumb sensors, was producing smart results. It was alive. It was the first faint heartbeat of a revolution, and I had the data to prove it. The flickering green vector on my monitor, the result of two cheap processors and a handful of salvaged sensors arguing their way to a correct answer, wasn't just data. It was vindication. It was the physical embodiment of my rejected theory, blinking defiantly in the sterile silence of my lab. But a blinking light in a cubicle doesn't win billion-dollar contracts. I had the proof of concept, but I was still Dr. Reed, the pariah, the academic dreamer stuck in environmental testing. How could I get this in front of someone who mattered, someone with the power to overcome the institutional inertia and the entrenched opposition of the Chimera Old Guard. Direct confrontation was suicide. Going back to the senior leadership with my "I told you so" data, cobbled together from unauthorized work, would result in my immediate termination, probably accompanied by security escorts and the shredding of my notebooks. I needed a champion. I needed leverage. I needed a crisis. And the Cold War, in its final, sputtering, unpredictable years, was about to provide one. While Chimera floundered, obsessed with its high altitude, long-range BVR, beyond visual range dual scenario against Soviet bombers, a new, uglier threat was emerging. Low-flying, terrain-hugging cruise missiles. Stealth technology was still in its infancy, but clever mission planning, combined with ground clutter jamming and the curvature of the Earth, made these small, fast-moving targets incredibly difficult for conventional, high-power, look-down radars to detect and track reliably. Reports started filtering back from naval exercises and intelligence briefings. Simulated cruise missile attacks were getting through the Navy's formidable Aegis defense system with alarming regularity. The existing Standard and Sparrow missiles, designed for high-flying fighters and bombers, struggled to acquire and intercept targets popping up over the radar horizon with only seconds to impact. The Navy was facing a critical vulnerability, a potential Achilles heel for its carrier battle groups, and they were desperate for a solution, any solution. This was my opening. While Vanguard's main Chimera team was still laser-focused on the Air Force's BVR requirements, I saw a niche. My distributed, multi-sensor approach, the one dismissed as stupid and unbuildable for the complex BVR fight, was actually perfect for the cruise missile defense problem. Why? Cruise missiles, flying low and fast, often presented fleeting, ambiguous sensor data. A brief radar glint here, a fleeting IR signature there, maybe a momentary ESM detection as the missile's own guidance system pinged the terrain. No single sensor could reliably maintain a track. But multiple, networked, passive sensors, each contributing its own uncertain piece of the puzzle, fused together using the algorithms I was developing, that could build a high-confidence track, quickly and covertly, allowing for a faster, more decisive intercept. The low-power, stealthy nature of my proposed system was also a huge advantage in a dense electronic warfare environment where blasting away with high-power radar just painted a giant "shoot here" sign on your own ship. I started tailoring my simulations, my algorithms, specifically for this anti-cruise missile scenario. I focused on fusing data from simulated ship-based IR sensors, ESM receivers, and even acoustic sensors, using a hypothetical, low-power, short-range radar only for the final kill confirmation. The results were startling. My simulated spiderweb system could detect, track, and generate a firing solution on a low-flying, terrain-masked target significantly faster and more reliably than the simulated conventional systems. But simulations weren't enough. I needed hardware. I needed a demonstration. I needed to get my prototype out of the lab and into a real-world test. This is where Ben Carter, my reluctant technician ally, became indispensable. Ben had connections, deep, greasy-fingered connections, throughout the sprawling military-industrial complex, especially within the Navy's test and evaluation community, where he'd worked before coming to Vanguard. He heard the whispers, the panic, about the cruise missile threat. He also heard about a specific Navy program, a low-priority, underfunded project called Shipboard Integrated Defense Initiative, CITI, which was tasked, vaguely, with exploring novel sensor integration concepts. It was a backwater ignored by the big players, precisely the kind of place where a radical, potentially embarrassing idea might get a hearing, especially if it promised a cheap solution to an expensive problem. Ben made a call. He called in a marker with an old Navy buddy, a chief petty officer running the CITI sensor test range at China Lake. He didn't pitch my whole system, just the fusion aspect. "Got this crazy civilian doc here," Ben had apparently said. He recounted the conversation to me later, grinning. "Thinks she can fuse IR and ESM data streams on the cheap, maybe get a better track on those damn sea skimmers. Got some home-brew hardware. Looks like crap, probably won't work. But maybe worth a look." The chief, desperate for any potential solution to show his own skeptical superiors, agreed to a non-standard evaluation. No funding, no official sanction, just a "come on down, plug your junk in, don't blow anything up" invitation. It was the break I needed. For 2 frantic weeks, Ben and I worked around the clock, adapting my lab prototype. We ripped out the strap-down IMU, irrelevant for a shipboard system. We built new interface boards to accept the simulated digital data streams representing standard Navy IR and ESM sensors. We refined the fusion algorithms, focusing on clutter rejection and track correlation in a maritime environment. We bolted the entire ugly mess into a ruggedized transit case, praying it would survive the truck ride to California. The demonstration at China Lake was surreal. We weren't in a gleaming control center. We were in a dusty, sun-baked trailer filled with obsolete test equipment. The targets were simulated data feeds played back from tapes of previous failed Aegis tests. The audience wasn't admirals, but a handful of skeptical Navy technicians and one weary-looking commander, the city program manager, who clearly expected nothing. I plugged in my box. I booted up the system. I fed it the simulated sensor data, noisy IR tracks, intermittent ESM bearings, ghosts, clutter, jamming. On my cheap monochrome monitor, the raw data was chaos, a blizzard of false alarms and fleeting contacts. Then, I enabled the fusion algorithm. The screen flickered, and then, order. A single, clean, stable track symbol appeared, cutting through the noise, representing the simulated cruise missile, holding steady even as the individual sensor inputs flickered and dropped out. It wasn't just tracking, it was predicting, extrapolating the path based on the fused data. The Navy techs leaned closer. The commander stopped tapping his pen. "Run simulation sequence Delta 5, the commander ordered, naming a particularly nasty scenario involving multiple targets and heavy jamming that had consistently baffled the Aegis system. The tech fed the data into my box. The screen erupted in clutter again, then resolved. 2 stable tracks, one designated high confidence, the other medium. It correctly identified the primary threat and ignored the decoy. "Holy," one of the techs breathed. The commander just stared at the screen, then at my ugly humming box, then at me. "Dr. Reed," he said slowly. "What is this thing?" I explained. "Distributed processing, sensor fusion, low-power UWB potential, though this demo wasn't using UWB. Collaboration between dumb sensors to create smart results. I didn't mention Chimera. I didn't mention my rejection. I just presented the solution to his problem." When I finished, the commander was silent for a long moment. "The big contractors," he finally said, "they tell me this kind of fusion requires cray supercomputers, neural networks that won't be ready for a decade. You're doing it in that?" He pointed at my box. "Yes, Commander," I said. "It's about the architecture, not just the processing power." He stood up. He walked over to my humming box. He put his hand on it, as if taking its pulse. "Dr. Reed," he said, turning back to me, a new, intense light in his eyes. "Project Chimera might be the Air Force's golden child. But the Navy needs to stop cruise missiles. Yesterday, he made a decision. I'm classifying this demonstration, top secret. You," he pointed at me, "and your technician," he nodded at Ben, "are now TDY, attached to my program. Effective immediately. Your company," he added, a predatory glint in his eye, "will be receiving a small, sole source contract for advanced sensor fusion algorithm development. Phase 1, enough to keep you funded, keep you quiet, keep you ours." He grinned. "Welcome to the Navy, Doctor. Don't screw it up." Just like that, my rejected blueprint, my stupid prototype, ignored and ridiculed by my own company and the Air Force, had just found a new home, a powerful new sponsor, and a critical new mission. The billion-dollar contract wasn't signed yet, not by a long shot. But the fuse had just been lit. The late-night sketch was about to go to war. The Navy contract wasn't just a lifeline. It was a declaration of independence. Vanguard Aerospace, my own company, was suddenly in the awkward position of having the Navy fund a secret, competing guidance philosophy within their own walls, developed by the very engineer their star program had ostracized. The internal politics were fascinating. The Chimera leadership couldn't kill my project. It was Navy-funded, classified above their pay grade. They couldn't steal it. The commander at China Lake had made sure the intellectual property trail was locked down tight. All they could do was watch, with a mixture of fury and dawning horror, as my stupid prototype started evolving at lightning speed. Freed from the bureaucratic inertia and the rigid dogma of the Chimera program, working directly with the Navy's city team and operators who desperately needed the capability, Project Spiderweb, now officially, boringly, designated Project Sea Nettle, flourished. We didn't have Chimera's billions, but we had something better, a clear mission, direct user feedback, and the freedom to fail fast and iterate. Ben Carter became the integration wizard, figuring out how to ruggedize our components, how to interface with existing shipboard sensors, how to make the system survivable in the brutal maritime environment. I focused on the brain, refining the fusion algorithms, developing sophisticated electronic countermeasures, ECCM, logic, optimizing the code to run on increasingly powerful, but still relatively modest compared to Chimera, embedded processors. We tested constantly, not just in simulations, but with real hardware, using drone targets, jamming pods, anything the Navy could throw at us at the China Lake range. The results consistently outperformed expectations. Sea Nettle could track sea-skimming targets in heavy clutter that left Aegis blind. It could distinguish decoys from real threats. It could maintain lock through intense jamming. It wasn't perfect, but it was resilient. It was adaptive. It worked on the principle of collaboration, not just raw power. The word started to spread, quietly, through the classified channels. The Navy, initially just looking for a niche fix, began to realize they had stumbled onto something much bigger. This wasn't just an anti-cruise missile system. This was a fundamentally new architecture for sensor fusion and networked guidance applicable to any missile, any platform. Meanwhile, Project Chimera continued to founder. Its massive, centralized brain remained vulnerable to sophisticated ECM. Its reliance on active radar made it detectable, targetable. Costs ballooned, schedules slipped. The Air Force, facing budget cuts and the embarrassing success of the Navy's Skunk Works project, started asking awkward questions. The tide was turning. The legends who had mocked my napkin sketch were suddenly finding themselves defending their increasingly obsolete approach against a system that was smaller, cheaper, stealthier, and demonstrably better at the hardest parts of the guidance problem. The tipping point came during a major joint exercise, Fleet Guardian 87, a simulated saturation attack, involving multiple waves of sea-skimming missiles and heavy electronic jamming, completely overwhelmed the carrier battle group's defenses, except for one ship. The USS Vincennes, a Ticonderoga-class cruiser equipped with the only prototype Sea Nettle system, achieved an unprecedented intercept rate, successfully tracking and engaging targets that the rest of the fleet couldn't even see. The data was undeniable, indisputable, classified but explosive. Within months, the fallout was seismic. Project Chimera, Vanguard's multi-billion-dollar white whale, was quietly, brutally canceled. Heads rolled, careers ended. The brute force, centralized processing approach was dead. And Vanguard Aerospace, facing financial ruin and public humiliation, received a new, even larger contract. A sole-source contract from the Navy, co-funded by a suddenly very interested Air Force, to fully develop, weaponize, and produce the guidance system based on Dr. Evelyn Reed's advanced distributed multi-sensor fusion architecture. My late-night napkin sketch, my stupid prototype, had just become the foundation for the next generation of American missile technology. The contract, initially valued at just under $1 billion, eventually grew, spawning variants, upgrades, spin-offs. The AMRAAM, the SM-2 Block 4 elements within Tomahawk guidance, fundamentally changing air-to-air, surface-to-air, and even strike warfare. My name never became famous like Kelly Johnson's. But every time a pilot trusts a missile to hit a target obscured by jamming, every time a ship defends itself against a sea skimmer popping over the horizon, a little piece of that stupid, coffee-stained napkin sketch is riding along, keeping them safe. They laughed me out of the room. They called my idea impossible. But in the end, the physics didn't care about their opinions. The future arrived anyway.